In this video, I will show you how to do correlation analysis in image matrix. So basically, correlation analysis is analyze a group of images or a group of particles that have periodical structures. So they basically repeat themselves, and then you want to analyze the patterns of these repeated patterns. So I'm going to use some examples to illustrate how this works. So there are various correlation methods and ways to do this. So let's first see. I'm going to do one first. I'm going to demo the correlation averaging of images. So these are taken in solution DNA sample, and so they used fast scanning. So you see that image quality is not very good because it scans very fast, but you can get a lot of images at the same time. So what I'm trying to show you here is so this is the height. So you see there's a lot of noise, and I try to see if correlation averaging of all these images can improve the signal to noise ratio or not. Specifically, I would like to do the phase, because the phase, you see, it's less noisy, but the signal to noise ratio is really low. So I want to see if after applying the correlation averaging, whether I can improve the signal to noise ratio on the phase. So what you do right now is you can click. So you use the options in the correlation analysis panel. You click image, and then apparently you want to select all the images to do correlation averaging. You select phase trace, that's fine. And do you want to output a correlation map? You can yes or no, it doesn't matter. So let's see the correlation map. Let's say yes. And I'll input the threshold numbers. So this is only useful for identify periodical features, because we're not doing any periodical studies. So this threshold number is only used for you if you have repeated structures in one image or multiple images. But this one is we're only doing like non-periodical features. So well, I guess you can do that as well, but because we're not input any threshold, we just want to average all of them regardless of their threshold, right? So I guess I just ended nothing, right? So then you can draw a area, because there might be some drifting among scans. So you want to pick up an area that's smaller than your image. Let's say that's this area that you want to average, and then double click. And the program should start doing something. Yes. So all images are successfully matched. So this is the averaged one. Let's do this. Let me just, for a comparison purpose, I'll just export this image and then put it on this side right now. And I'm going to see what has happened. So you see in the image channel, in addition to the image that we open, we also have a correlation map, a new image called correlation map, and another image called correlation. Let's say the correlation map. So the correlation map is basically what I did just now is I pick up a template image, right, and I match the template with all the other images. So when the template tries to match each one of the image, it outputs a correlation map. That's why you see that there is one correlation map for every one of the other images in this group. So as you see the correlation map, there's a bright spot in the center, which means these images are pretty much in the same spot, so there's not much drifting, so that's expected. The bright spot will indicate that's where the template matches best with the images, right? So this is the correlation map, and so if you want to understand more how correlation cross correlation works, you can read other literature. But I just give you some idea of how the correlation works in this program. So there's the other image is called correlation to, it's just a correlation image. So with this one, what you have is you basically so you see here the naming of this channel. So it's composed of several parts, right? So the first part is the name of the image, and 18 would be the template that we use, and the second part is the data channel that we used for the template, which is phase trace. And there's a third part which gives you the correlation coefficient. So as you see here, that 1 means that it's perfectly matched. It's not surprising because that's the template that we use. It definitely matches up the, perfectly with itself. So that's 1. But when you try to use number 18 as the template to match other images, now you get a small correlation coefficient. So you see that about 0.2 to 0.3 ish. So if you click the other images channel, so you see, then you can just go travel, through these. So you see they actually match up pretty well, and this little shifting locations, it means the program find the correct patterns in the other images. And finally, we have a standard deviation and correlation averaging. So it's the standard deviation should be, if the images are matched up pretty well, the standard deviation should be pretty small, and it looks like that's the case. And the correlation averaging, I just export this image. So let's pick out any of the region image, which is 18, right? What you do is, I would not like to use auto scale, which might confuse a few things. So just untrack the auto scale there, and let's redo this again. So we export this image, graph the image, and then go back to the correlation average results and the export image. I might be able to tune the scaling a little bit better, but for now that should be fine. So you see the original image, the template is pretty noisy, but the average one is significantly better signal to noise ratio. So this is for the correlation averaging of a group of images, which is useful for enhance the signal to noise ratio. It's also useful, so it's pretty useful if you have images that have higher noise and you want to, in FM, right, you can improve your image signal to noise ratio by repeatedly scan the same area. So that's a useful part. It's also useful if you have, like in this case, it's image in solution. So in my experience, you might observe dynamics of this DNA molecule in solution. So when you average these, the thickness of the DNA, which if you have dynamics and DNA won't average well enough, then you would observe it moves. So the signal could be diffused, and you will observe those dynamics as a function of how diffusive your DNA is and the average image. So the other benefits of using correlation averaging is you can use it to analyze image drifting. So it's useful in solution as well. I mean, especially if the image, sometimes it's the sample that's drifting, sometimes it is AFM scanner that's drifting, so it's not perfect work. So you might want to correct the AFM scanner drift, and that's useful, and I'm going to show you in a second example. So let me close all these images for now and just open the image drifting example. So I have a group of images. So let's turn on auto scale for now. So you see that I just go through these images. So you see as the particle is definitely drifting upwards to the right. So I want to correct the drifting so that I can see the dynamics better. So for example, I want to observe this part of the molecules. See, so if they are drifting, it's hard to see whether they really move or not, but if you can correct the drifting, you might be able to see the real movements that's not drifting related. So all I need to do is to click an image again. So there's some details about what's done behind the scenes. So I will talk more about that in the menu. So apparently, there are various correlation methods, and you will have to understand the method behind it. Really understand how the correlation is done, right? So, right in this example, it's using normalized cross correlation. So that's the method that we use. So that's one of the reasons I don't need to flatten image, even though the image they have different scales, different relative height, but that's not important because in the end it's normalized. It's called normalized cross correlation. So the method is independent of like the offset of the image, so you don't have to worry about flattening. But if you want to do some perfect matching, you might still want to flatten the image, but right now it's not necessary. So select all these images, and then select height. And if you have like double like trace and retrace, you can actually select two traces, two channels at one time, and they can be matched. So it's basically in some AFN you can scan both the trace and retrace. So you basically get two images in one scan, and that's pretty neat because it always can improve the signal to noise ratio by using two samples, right? Instead of just one. So I just click retrace, say yes, and in this case it's still it's not a periodic structure. So now you can crop an area, so just crop this area, that's what we want to match, and then just double click. So our image is successfully matched. If there are outliers, it will tell you like which image is not matched and excluded. So right now I have the average results, seems pretty fine. So I won't go through the correlation map, which is useful as well. You can see like let's see the correlation map first. So what I would like to do is I want to increase this. Yeah. See, so the mask can tell you like what's the highest point in the threshold. So you can see that it seems the first one, yeah. So there's a match. You see here in the center, that's where the spot is. That's where it matches with the template. So then you can go through various other images, see if they have a sense. So you see that this spot moves upwards. So it means the template moves because the image is drifting. So it looks like the algorithm works pretty fine, and then it moves further upwards. So I have to go down a little bit. See that? And upwards. So you can always find a bright spot in the center. Remember that although there's spots elsewhere, but they're not really counted into this algorithm. There's a cutoff region, so you don't have to worry about them. All this I'm trying to show you is that the algorithm correctly identifies the peak of the match, and see the spot moves as the image is drifting, so it finds the correct match. To verify that the match is perfect, you can go to the correlation and then check individual images. The first one is the template, and then we go through this. So this one apparently identifies that these are the same spot that's in different image, but they apparently have moved the space, but the software identifies them and extract them. So and in the end, all these images, because they're similar, they will be they're matches, right? They will be averaged. So the last thing is standard deviation. Apparently, this particle, even though the drifting is corrected, still has some kind of movement. It means that there's some dynamics. Instead of not like the last one that we did a phase, we don't see any kind of standard deviation. But this one we see some standard deviation, which means there's some kind of dynamics of this molecule, and in the end we can do the correlation averaging results. So let's do this. Let's just export this image, the correlation average one, and go back to the template and the export image. Do a side-by-side comparison. That's the template, and that is the average result. So you see that apparently the template and the average result are not exactly the same, and apparently the average result is kind of a truncation there, which means that the DNA molecule, there's some dynamics in that region. That's why it's not added up. Instead, they kind of cancel each other. That means there's some dynamics, at least at that area of the DNA molecules, that specific arms there. It kind of disappears because some dynamics also appears to be that the same to the top of this circular DNA. So this is very useful, especially if your molecules are drifting. That can be corrected in this example. You also can observe some dynamics. If they don't add up perfectly in the average results, you see them disappear instead of enhanced, and I mean there's some kind of dynamics of the DNA molecule. So these are the examples of correlation averaging used to enhance signal-to-noise ratio, to analyze dynamics, to if the dynamics see a decrease in signals, if they are stable, you get enhanced signal-to-noise ratio. So these are pretty useful. So finally, I'm going to show examples of how to use correlation averaging in periodic structures, especially in protein crystals, and all kinds of other images where you have even the specific advantage of image metrics is that can be used to analyze images that are not protein crystals. So, which means the particles that can be randomly aligned, but the image metrics has the powerful rotational correlation algorithm to identify them and realign the particles, and see if they, so essentially make unaligned particles realign again as if they are protein crystals. So yes. So first I'm going to show you a demo of the it's kind of like a crystal periodic structure. Let's do this. I think I need to do some options there. I should check this one, and the Oh well, I'm trying to open this image. It looks like it's not opening, and I think there's something. Let's try this again. Maybe it's the wrong one. Let's do this. Apparently it's still not opening for some reason. And now I can close it. Oh, anyway, it's opening right now. So this is a text file. Need some data import. Maybe there's some issues here, but I'll check them later. Make sure it works. I just closed it again. So all right. So this right now should work fine. Yep, there you go. Let's try to fix it. Excuse me. Alright, so we have a periodical structure image. So apparently there's some kind of noise, and I would like to get an average result of these, and to improve the signal to noise. And that should improve the resolution significantly. So all you need to do is to click the image again, and so this is one example. Maybe I should use some better examples, but let me see. This is a fine example. Well, why not we use something that's more interesting? So I think I would have those. Oh, there we go. I just go on to website download some nice periodical images so that we can do some real examples, not that one. Try to open a science research website, which is the manufacturer of AFN. That's interesting. It did not open. Huh. Thought I have an internet connection. Maybe I should debug this. Yeah, anyway. So let me just use this example. I don't know what the sample is using right now, but just assuming it's a protein crystal. Okay. So there are multiple ways to improve the signal to noise of protein crystals. So one thing can be Fourier transform. You click FFT there, it give you a signal, a Fourier transform of these. So you see the periodic structures, the enhanced signal peaks in FFT. You can mask the region that's not periodical, which is not there's low background frequency there's low background noise, so signals, and they only use the region of these high signals in the FFT to do the inverse FFT. So that's one thing. This basically you can basically only keep the periodical structure signals, but remove all the other signals that's not periodical. So this is one example that you can use FFT to improve the signal to noise ratio, which I think I show you the example when I talk about FFT in image correction. So you can, if you have questions, you can refer to that tutorial. So that way, so once you have done the FFT, just to remove things, you can then do the correlation averaging, but they are independent methods, so you don't have to, you can apply them both, but you don't have to do FFT in order to do correlation averaging. So for now I'm just doing the correlation averaging and see what it looks like. So do the correlation averaging, I mean essentially when average results, the noise will be, they're not periodical, that will be decreased, and it will still increase the signal to noise ratio, so you probably don't need to do any kind of FFT to remove unnecessary other signals. So to do the correlation averaging, you click image. There's only one image here. You can actually open two images. That's fine. Do an RMS and let's say 0.7 for the correlation. But just an empirical number. You can, well, if you choose a higher number, then so this is a threshold that I'm talking about earlier. So because this is a periodical feature, you have to, if you want to analyze periodic feature, you have to enter some threshold numbers. This threshold is from 0 to 1 is basically a correlation coefficient. So basically, then the program lets you choose a template within the image. So you want to move the template around to match elsewhere in the same image, and when they match, they will produce a correlation coefficient which is rated from 0 to 1, and you define like what's the threshold for that number that you can use. It's only the match is above a certain kind of threshold where you use them as a match, where we classify them as a match, otherwise they're not matched. So this is basically give you some kind of control what's matching, what's not matching. So typically the higher number, the more quality you have for the matching. So the 1 will be only matched with itself, right, the template. So if you use 0.7, which will match pretty well, I mean the match should be quality, of high quality. So if you use like 0.3 then 0.2, then the match will be pretty bad, and you probably won't get a good enough averaged result. So I use 0.7 here, and then I draw a area, just draw a unit cell, right? Just any template that I want to average, just double click this area, and this is averaged. So it's the same thing. But right now let's see the correlation map first. So you see that this is correlation map because we use 0.7. You can specify the mask stress as 0.7 just to see better which ones are matched. So right now you see there are those in isolated mask area, they are the matches, and apparently we have a lot of matches there, and almost each individual cell that match, and that's the pattern showing up in this original image here as well. So then we go to inspect individual matches. So you can go through all these matches. So this comes through. So apparently the match the algorithm find the matches pretty well. So they're noisy, but it's expected. But it does find there's very minimum drifting locations. But eventually you want to extract the standard deviation, which is pretty fine. So there's no high spot, and then check the correlation averaging results. Let's do a comparison again. So export this image. This is the average results. Oh, I made a mistake. So then I go to the template, which is number 1 here, coefficient, and then export this image. So you see that the template is noisy and the average results is very refined and apparently improve the signal to noise ratio greatly. So this is to analyze periodical structures. So, and that's pretty standard in this field, found in EM. But what if we have randomly distributed molecules that we want to analyze to align them, okay, and average them? So that's a not, it's not new to EM, but it's not new. Okay, I mean it's new I think in the AFM studies. So what you do is you can I'm going to show you an example. I open one image that has this period, those randomly aligned. This is a protein, so you see the protein just randomly deposit on the microsurface, and you can see them. Let me just do one thing, scale it a bit better. So you see they are randomly aligned, and oh, I forget one thing about autocorrelation. So you can also do an autocorrelation of the image if it's periodical, but I didn't do it here, but you can find out what it does when you do your own application. So so we have right now randomly aligned molecules, right? And basically I want to realign them in a certain axis. I mean the same axis, and then so I can average them. For example, there's some molecule like this one and that one. There's 2 parts, and they're pretty much the same like that one. So, but right now I can't average them because they are oriented in different directions. But using my program, the image matrix, you can realign them in the same direction, then you can average them. So this is pretty powerful technique. So what you do, you can use the options in the correlation analysis panel. You have apparently a lot of parameters you can choose. I won't explain the parameters right now, so I will explain them more in detail when you can read them manually. It's there. So basically, the one parameter I want to specify is rotation intervals. That means basically what the action does is it rotates every molecule, and so you have to pick up it. So when you analyze one molecule, it rotates all the other molecules and try to find the perfect match. So when it rotates at a specific degree, you can choose the rotation intervals. Apparently, it can rotate like continuously. It rotates at some discrete numbers. So when you rotate the molecules and the software will calculate the correlation coefficient and until it finds a perfect match. And not a perfect match, but it finds the maximum quality of the match. So basically, if you rotate by 2 degrees, apparently has rotated a foreground which is 360 degrees. So if you rotate by 2 degree interval, you basically have to rotate one molecule 180 times. So you calculate 180 round of correlation coefficient. From that 180 correlation coefficient, you pick up the maximum one. Then you can determine which angle of rotation that gives you the best match. So that's basically the underlying mechanism how this algorithm works. So once it finds the correlation coefficient, it records, then it gives you assigns a number to the particle pairs, what I call. So you calculate the correlation coefficient between 2 particles. Basically, it determines every pair and calculates the correlation coefficient of every particle pair, and rotate them and calculates the correlation coefficient. And you can also choose these the method of them and whether it wants to do auto correlate, crowd particle or manual defined region. I'll expand all of these in the menus, but I need to do it right now. I mean, typically, if you want to save some time, you can do a symmetric calculation and how to show progress. You can also do parallel computing if you want, and if you have multiple core system, it helps improve the calculation speed. And you can also do directional calculation, and you can also do offline analysis if you want to calculate it on a MATLAB server. So it's like use a cloud computer to calculate them, which significantly improve the speed. So yeah, and if you want to do just a rough matching, you can do 10 degrees instead of 2 degrees. Basically, it proportionally improves scales your speed of calculation. So at this moment, I think apparently you have to analyze the image first. Let's just do a quick analysis of this one. Flatten them. Analyze them. Yeah, so once you analyze them, you can do the correlation calculation. And this time you have to click particles, okay? If you're not analyzed, this option is grayed out, so you can't use it. Right now I can, so I just click particles. Yeah. And then I think everything's good to go. So it's calculating. It will start from the particle 1, which is this one, and then calculates correlation coefficient with all the other particles, which is the other 91 particles. Then once it calculates, it basically rotates every other particles about 18 times, because I use 10 degree intervals, and calculate the correlation coefficient of each rotation and determines which one has the highest correlation coefficient. And then it picks up that rotation angle and assign this to the particle 1. So you see it goes to number 2 particle, now it's calculating particle 2, and now it's calculating particle 3, and so each particles will have a corresponding particle pairs, right? So the 1 will pair with 2, and will pair with 4 with 3, and so on and so forth. And so for each pair, the particle pair has a correlation coefficient assigned and a rotation angle assigned. So you get a table of this correlation coefficient table and correlation rotation table. So in the end, yeah. So I think that's pretty much, and it takes some time to finish. So I won't let it finish right now. But it'll go exponentially faster if you have the symmetric rotation and symmetric correlation checked. But anyway, so yeah, if you want to make it faster, you can check the parallel computing. I could check that, but I didn't do it. You can also do offline analysis if you want to calculate it on a server. So, alright, that's all for correlation analysis.